we're going to start on something new. I meant to have printouts for y'all, but I think everybody close your Chromebooks. But I think that we should be fine with just the one page on the board. It kind of sums up everything pretty nicely. So today we're going to finish up. Oh, I'm going to freeze. We're going to finish up this chapter for the periodic table, which is why I asked you all to grab a periodic table. We're going through periodic trends. And so with the periodic table, we've already established that it tells you a lot. Depending on which periodic table you have, it can tell you all sorts of stuff. This one, just by knowing where your element's at, tells you how many protons it has. It tells you how many electrons it has in its valence shell, how many total electrons it has, what kind of properties it has, whether it's a metal, a non-metal, a metalloid, whether it's radioactive or not. There's all sorts of things that the periodic table can tell you right off the bat. And we're going to go through a couple more of them today, including the atomic radius. So what is the radius? Yeah, half of the circle. So if I tell you, if different atoms have different radius, what does that mean for the atom? But I mean, if I change the radius on a circle, what am I changing? The size, right? The diameter, the radius is just half the diameter. So if my radius gets bigger, my circle gets bigger, right? Yeah. So the same thing happens with atoms. When we talk about atomic radius, we're talking about atomic size. How big is the atom? Ionic radii, same thing, but instead of an atom, it's an ion. So you have a couple extra electrons, which the electrons are on the outside. That will also change your size. Electronegativity is an atom's ability to, I believe, steal electrons. And then ionization energy is how well it gives up or steals electrons. So there's lots of different things that we're going to go over. The good news is these aren't specific numbers. They're just trends. And so you're just going to have to put things in order, like from most to least. There's not going to be any numbers. There's not going to be any math or anything like that. So periodic trends are the patterns of properties seen across periods and within groups on the periodic table. They show you the periodic table. It's useful for predicting properties of elements and best displayed in main group elements, meaning your S block, your P block, and your D block a little bit. Now, atomic radius. This is the size of your atom, how big your atom is versus how small your atom is. And this says decreases, and you can see it's real light over here, this direction, and increases this direction. So basically, the dark blue area is going to have your biggest radius. And as you come further this way, you're going to get a smaller and smaller and smaller radius. Does that make sense? So hydrogen is going to be bigger than helium as far as its radius. Whatever's over here, let's see. Potassium, K, over here, is going to be bigger than krypton. Over here, it's decreased. And so it increases as it goes down. It increases from right to left. And that is your general trend. So if they ask about how big an atom is, you just want to find out what part of the periodic table they're in. Like find all your atoms, and you're going to put them in order. If they give you like this one, that one, that one, and that one, you know that this one's bigger, and they're going to get smaller as they go up towards this corner. Is everybody cool with that? So just to show you as we go back, so you kind of see what you're going to have here. Your they have ionic atomic radii right here is in the yellow. It gets bigger towards this corner and smaller towards that corner. So you just need to figure out where they're at and kind of put them in order that way. Is everybody cool with that? So going back to the PowerPoint. Let's see what's next. Increases down a group, decreases from left to right. Atomic radius, decrease from left to right across a row. We've already talked about this. Positive charge of nuclei increases from left to right. Elements further to the right have more protons in their nuclei, drawing electrons in closer, resulting in smaller atomic radii. So that's why you see that trend of them getting smaller on this side, because as you go from left to right, you get more and more protons. The protons are positive. They're going to attract those negative electrons in closer to them. Even though they have more electrons, they're pulling them in closer. And then you get to the next group, you have less electrons, and so they kind of space out a little bit, and they're further away from the protons. So that's why it goes that way. Atomic radii increase down a group. The elements towards the bottom of the periodic table contain more electrons in their more energy levels, and so they're just going to be bigger. Now, at a certain point, they introduce shielding. Basically, what shielding is, if you have so many electrons, like let me draw this for you real quick because I don't think they have a picture of it. You have your nucleus here with all your positive protons, right? And the protons pull the electrons that are in your close groups in closer and make your atom smaller by attracting them in. If you get a certain amount of groups with just electrons kind of everywhere, these electrons will kind of block out that negative or that attraction to the protons for your outer electrons that are further out. So on this outer shell, if you have a whole bunch of different shells of electrons, they're going to kind of shield these outer electrons from the pull of the protons, which is going to help the atom be bigger. And so that's what shielding does. The phenomenon in which electrons in energy levels act as a shield, preventing the electrons in the outer energy levels from feeling that pull and being pulled in closer to the positively charged nucleus. Does that kind of make sense a little bit? Hey, make sure your head's up. So, more layers of electrons result in more shielding and a larger radius, which is why your bigger stuff at the bottom has a larger radius. So, ionic radius. This is the same thing, but for atoms that are charged. So they have not an extra proton. They have more or less electrons than they're supposed to be. They have a positive or negative charge. The approximate distance from the nucleus to the outermost electrons of an ion. Their example here is, this is normal lithium. This is lithium with a +1 charge. This is normal sodium. This is sodium with a +1 charge. So if you have a +1 charge, everything is a little bit smaller. If you have a -1 charge, everything is a little bit bigger. Does that make sense? Because if I get rid of electrons, I have more pull from my protons in the nucleus. It's going to pull everything smaller. If I add more electrons, it's going to give me more shielding. It's going to stack more electrons in outer layers. They're going to be bigger than they should be. So that kind of makes sense a little bit. Cations are smaller than their neutral atoms. Anions are larger than their neutral atoms. So we see that here. Cations are positive. They're going to be smaller. Anions are negative. They're going to be larger. Anions have a larger radius than cations in the same period. So these are your periods. Your anions that are negative are always going to be bigger than cations that are positive in that same group. So for ionic radius, it's a little bit different. If we go back to the chart here, anion radius gets bigger just for these like 3 or 4 rows, because these are only going to be negative. Once you get to like this row right here and go to the left, they're going to be positive. So your anions get bigger this way, they get bigger this way, and they get bigger down towards the bottom. But know that your negative atoms are usually larger than your positive atoms. So if we come back here, you can see that they get larger this direction, they get larger this direction as positives, and they get larger towards the bottom as you go down. These are already large, so it's kind of hard to tell, but you can see they get bigger as you go down, and they get bigger as you go from left to right. So, next. Decrease, yeah, we already said that. Now, electronegativity. What electronegativity is the measurement of an atom's ability to attract electrons or steal electrons from other things. So if you imagine this, your atoms that have 7 out of 8, like your chlorine, bromine, fluorine, they are really good at stealing an electron. They only need 1 to get up to 8. They already have 7 out of 8, so they're going to be really good at stealing electrons. They're going to have a high electronegativity. Over here towards the left, lithium, sodium, potassium, rubidium, they only have 1 out of 8. They're not good at stealing electrons at all. They almost never steal electrons. They are good at getting rid of electrons, giving them up to other atoms. Keep your head up. Keep your head up. They're good at giving up their electrons, so they're going to have a very low electronegativity. So low electronegativity over here, high over here, and then going from bottom to top, it says it decreases. Is that right? No. Well, it says decreases as you go down, but it increases as you go from the bottom to the top. You can see AT down here is lighter shaded than F is. So It's going to go from this corner is the lowest up to that corner is the highest. And again, you see that over here, electronegativity and ionization energy, smaller down here in this corner, larger up here in this corner. So now we just got to go through ionization energy, and then y'all can start on the assignment. Yeah, we got that. Noble gases aren't going to be included in that because they already have 8. They're not giving up or taking in electrons at all. Ionization energy is the measurement of the amount of energy required to remove one electron from neutral gases, gaseous atoms forming a cation. So how easy is it to remove an atom? If it's really easy, it's not going to require much energy. So you don't have to put much in. If it's going to be difficult, you're going to have to put a lot of energy into taking those out. And so when we get to this, it's kind of the same thing. These atoms over here, which are really good at stealing electrons, aren't going to want to give them up at all. You're going to have to put a lot of energy into taking an electron out of like a noble gas or like chlorine, which already has 7 out of 8. It doesn't want to get further away from 8. It wants to get closer to 8. So you're going to have to put a lot of energy into taking these, where your alkali metals and your alkali earth metals, they'll just give up their electrons easily. They'd want to get rid of them to get down to 0. So it's not going to take you very much effort to be like, hey, give me your electron. Okay, I got you. And then it's done. And so these over here have low ionization energy. These over here have high. And so back on the chart, you see that those are on the same little run right here. Now let's see. I think we're towards the end. Let's see what else they have to say. Value for ionization energy is related to how strongly atoms hold onto its electrons. Trend opposite from atomic radii trend. Noble gases have the highest one because they already have 8. They don't want to get rid of any of them. So I'm going to leave this up while you do the assignment. I need to open up the assignment, and I will post this to Google Classroom very quickly so you can kind of use that. But I don't think the assignment is too difficult. At least there's no math or anything else crazy going on. So